Hello, everyone. Welcome to the Unit 4 test review. Let's just get right into it, shall we? So number one, what does DOFS stand for? DOFS, as you know, hopefully know, stands for, D stands for direction. O stands for outliers. F stands for form. And S stands for strength. Those are DOFs: direction, outliers, form, and strength. And this is, if you ever describe a scatter plot, this is how you describe a scatter plot. You talk about those four things. So this is a little acronym to remind you how to describe a scatter plot. All right, match a statement. So if R is equal to 1 or -1, it is a perfect fit. So that would be matched to A. If it's close to -1 or 1, then it is a good fit. That would be B. If R is close, or if R is equal to 0, then it's no correlation. That would be C. If it's close to 0, then it's not a good fit. If it's less than 0, it is negative. And if it's greater than 0, it is positive. So those are the associations there, right? That's the R value. Remember, the R value ranges from -1 to +1. And -1 and +1 are perfect correlations. And the closer you get to 0, the weaker that correlation gets. So that's the connection with all those. A correlation of -0.36 is stronger than a correlation of 0.33. And that's because it doesn't matter if it's negative or positive, the larger number is stronger, essentially. So like, if this is closer to quote 1, right? Closer to -1, yes, I get that, but it's closer to 1 than 0.33 is, right? 0.36 is closer to 1 than 0.33. So this is closer to this is a stronger negative correlation. This is a weaker positive correlation. But we're not interested in negative or positive. We're just interested in what's stronger and what's weaker. So 0.36 is stronger than 0.33. What does each part of the equation of the regression line represent? So y hat is the predicted y value. A is your y-intercept. B is the slope. And the x is the x value, basically. Nothing really special with it. Yeah, because the x value is normally what you plug in, right? It's the input variable or explanatory variable, just the one that you plug in. Number 5. So we're writing an equation. It's going to look like this, but it's going to have a slope of 4. So the b value would be 4, and a y-intercept of -9. So the a value would be -9. So essentially, the equation will look like this: y hat equals -9 plus 4x. So 4 is the slope number, which again was the b number, and the -9 was the y-intercept, which is the a number. So obviously a little typo on this. This question is the test question, but it has the wrong graph because I changed the graph. I meant to change the words here and I forgot to. But the question is basically, does there appear to be a relationship between should be basically gender and favorite sport? So between favorite sport and gender. So that's what we should change these to, between favorite sport and gender. So we look at this graph and we say, hey, is there an association between favorite sport and gender? And we would say, yes, there is an association. Yes, because the proportions are different, basically. I'll just keep it short and sweet for now, but basically to summarize it a little longer, yeah, the proportions of male to female and their preferences change for each sport. So football, you've got more male enjoyment, more male preference, but baseball, you got more female preference. So there is a distinct difference in their preferences. So yes, that means there is an association between their sport that they like and their gender. The least squares regression line is a line that makes the sum of the squared residuals as small as possible. Sum of the squared residuals as small as possible. Basically, comes straight out of the 4.6 notes. Number 8. What is the equation to find the residual? So the residual is equal to the actual y value minus the predicted y value. So sum it up, it's y minus y hat. Essentially, again, actual minus predicted. Number 9, standard deviation of residuals is closer to 0 is best. A smaller standard deviation means the points are more compact and close together. And if they're more close together, then that means there's a stronger relationship there between the variables. So standard deviation closer to 0 is best. All right. So this one, a student needed a calculator for her stats class. She collected selling price and number of bids received from eBay.com on the same model of calculator she needs to purchase. The equation of the regression line is that, where X is the number of bids received and Y hat is the predicted selling price. Calculate and interpret the residual for a calculator that received 32 bids and sold for $73. So an actual calculator had 32 bids and sold for $73. It's the actual selling amount. But we want to compare for residual, we want to compare that actual to predicted. So if we took 32 bids and we plugged it in, what would be the predicted selling price of this calculator? So 60.386 plus 0.322 times 32. So I'm not going to pull my calculator up because sometimes that like messes with the computer. So I'm just going to use my calculator that I have in hand. You can hear me using it. And I'll just type it in that. But yeah, basically just type this in 60.386 plus 0.322 times 32. We get 70.69. So actual minus predicted, we have 73 minus 70.69 is our equation. Remember, again, it's always actual minus the predicted. So this comes out to, I think, $2.31. It's positive, which indicates to us that this calculator sold for $2.31 more than predicted. Calculator sold for $2.31 more than predicted. All right. Big thing there to remember is once you plug in the 32 and you find the predicted amount, remember it's actual minus predicted, not the other way around. If you do it the other way around, you're going to have the wrong answer. Number 11, there is a relationship between what year a college student is and their opinion about whether parking passes should be given to freshmen. What is the explanatory variable and the response variable? So the explanatory variable is what year the student is in, year of student. And the response variable is the opinion of parking passes. So opinion of parking passes. So the idea is that the opinion of their parking pass situation depends on what year the student is in. So what year they are can help us predict what their opinion on parking passes is. All right, that is that. Number 12, what happens to our predictions when we extrapolate farther from the data we collected to create our regression line? So if we extrapolate, our predictions become I just had the word. I'm just drawing a blank now. What was I gonna say? I know basically predictions are less accurate. So I was trying to go for less accurate. Trying to mess up here. Yeah, if you extrapolate, the predictions become less accurate, basically. Outliers with relatively low or high X values. So basically an image of this is, imagine you have a scatter plot, right? And you have a outlier that is a really high X value, which would be like way down here somewhere. So like high on the X scale. So you can see on the X scale, way down here. So an outlier way down there, or one that's really low on the X scale. Could be like way over here. I'm not talking about high and low in terms of the Y. I'm talking about high and low in terms of X. So a low X value is near the beginning, a high X value is near the end. So what we're not talking about is one near the middle. We're not talking about an X value near the middle. But what these outliers would do, being on the ends, is that they'll affect these ends more. So like this outlier would drag this up. This outlier would drag this one down, essentially tilting the line. So that's the big thing here, is that those outliers on the edges have a strong influence on the slope of the line. So they will tilt the least square regression line, essentially changing the slope. Yes, the y-intercept will change a little bit too, sure, but the changing of the slope is the big thing. Number 14, a coefficient of determination r squared closer to 1 is best. Remember, this goes from 0 to 1, and it's better if it's closer to 1. It means it's a stronger fit if it's closer to 1. Here are 3 residual plots. Which of the residual plots indicate that the linear regression model is appropriate? B, because B is scattered. So that's the reason why. Scattered with no pattern. Scattered with no pattern is the reason why. Both A and C have an obvious pattern, but B is scattered with no pattern. That's why B is a good residual graph. All right, number 16. A politician wanted to know if there's a relationship between the amount of time he spent holding rallies in a city and the percent of votes he received from the voters in the city. A random sample of 9 cities were selected, the amount of time spent there in days, as well as the percent of votes received. Blah, blah, blah. The correlation came out to R equals negative 0.121. Which is not a very strong correlation. It's a very weak correlation. So which of the following is correct? If the time was recorded in hours rather than days, the correlation would be this. This is a false statement. This cannot be true. One, for a couple of reasons. One, correlation is only between -1 and +1. So to have a correlation of -2.9 makes no sense. Secondly, if we change the units, remember, changing the units does not affect the correlation. So if we change the units from days to hours or whatever, it would still be the same R value. So changing units does not change the R value. So that's why we want to draw. Plotting time on the vertical axis and percent of votes on the horizontal axis would not change the correlation. This is true. That's a good one. You can swap X and Y all day long, and the correlation would still be negative 0.121. Number 3, the correlation between time and percent of votes can be interpreted as negative 0.121% per day. This is incorrect as well because the correlation does not have units. So correlation does not have units. Correlation has no units. So negative 0.121 is all it is. It's not a percent. It's not days. It's not hours or minutes. It's just a number. It has no units. So that's why that statement is wrong. So just 2 is the only correct statement there. Number 17, which of the following scatter plots has a correlation of 0.986? So first off, I notice it's positive, which rules out this one. So because A is clearly negative. It's also a very strong correlation, which rules out this one. Because it's very strong, I'm going to pick C, which C is a good one because it's almost in a perfect line. D is positive, but it's a little more spread out. So I'm going to rule that one out as well. So yes, C, definitely the right answer there. Number 18. So many drivers want a vehicle with a lot of power. One way to measure engine size is by the number of cylinders in the engine. A vehicle with more cylinders has a larger engine and thus more power. How does the engine size relate to annual fuel costs? The scatter plot and regression equation display this relationship for all conventional fuel vehicles from the current year. The equation of the regression line is that. All right. Now, this one, there was supposed to be a graph that I printed off and I didn't for some reason, but this is the graph. So I'm going to refer to this as we need to. So let me go back to this. Calculate and interpret the residual for a vehicle with 8 cylinders that has an annual fuel cost of $3,100. Okay, so we've already done a residual question before, but we're doing it again. So we're going to plug in our x value into the function and see what the predicted amount would be. So y hat equals 826.066 plus 297.723 times 8. And so that predicted value of 8 cylinders, let's see, let's type this in. Is 3,207.85. 3,207.85. So that's the predicted fuel cost. And remember, this was the actual fuel cost. So the residual, remember, is the actual fuel cost minus the predicted fuel cost. Which comes out to, let's see here, negative 107.85. Which basically means that the actual fuel cost was $107.85 less than expected. There we go. So not too bad. Let's go on to part B. Part B says interpret the slope and y-intercept of the regression line. So the slope, it's gonna be kind of hard to write this. So let me zoom in a little more. Try to maximize my space. The slope was 297.723. 297.723. The interpretation of this would be as we increase engine size by 1 cylinder, we or I guess let's say the fuel costs, expected fuel costs increases by $297.72, basically. All right, and now the y-intercept. So the y-intercept number is the 826.066. And this means that with 0 cylinder car, with 0 cylinders, we would pay $826 in fuel cost. Now, I'm going to say no meaning as well in this. I don't really have enough room to write anything else. But it says, does the y-intercept have any meaning in this context? And no, because you're not going to have a car with 0 cylinders. I guess technically, actually, they have rotary engine cars. That's neither here nor there. So, essentially, no. You don't have a car. You don't drive a car with 0 cylinders. Let's just put it that way. And so, yeah, that kind of car doesn't exist. So why would we pay $826 fuel costs for a car that we can't drive? So, and C, luxury car brand Bugatti has a 16-cylinder engine in its sports model named Veyron. Would it be safe to predict the annual fuel cost for the Veyron with this regression line? So that goes back to this graph. This graph goes from 3 to 12, and we're looking to do 16. 16 would be way out here, which is extrapolating, and so no. So no, if we predict 16, we are extrapolating. Which is not reliable. All right, number 19. I gotta hustle this out. So here's a scatter plot of the fuel efficiency in city driving, miles per gallon, and weight in pounds of 2014 sedans. So 20 different sedans from the year 2014. The dot in the lower right corner represents the 2014 Bentley Mulsanne at the price of $305,000. Anyone buying it probably doesn't care about fuel efficiency. Correct. Describe the effect this point has on the equation of the least squares regression line. So this one right here. This outlier is, we kind of talked about this earlier, it's on the far right side. And it's above the line, which means it's going to tilt this line up. So this line without it would probably be more like this. But with that outlier, you can see it has to tilt that slope a bit. So this outlier tilts regression line towards it. Which is, it flattens the slope. Flatten slope. Making it closer to 0. Right? When I say flattens the slope, I mean, like I said, you can see the blue line would be the line originally without it. The red line is not as steep, right? So when I say flattens, it's not flat, right? It's not straight across, but it's less steep, I guess is maybe a better way to say it. All right, and last question. Basically, I'm not gonna read it because I gotta hustle this out, but we have the S is 105.5 and the R squared is 0.423. It says interpret these values. So S 105.5. Oops. The interpretation of this is that what was the wording of this? It was, give me 1 second, trying to think back to it. The actual calories is typically about 105.5 well, it's not calories. What was the y variable again? The y variable is, yeah, number of calories. Calories off from the predicted amount. So that's our interpretation. The actual calories is typically about 105.5 calories off from the predicted amount. That is our standard deviation. Now the R squared value is 42.3%. And this is because, again, you convert this into a percent number. Ooh, 1 second. All right, sorry about that interruption. So anyway, we convert that 0.423 to a percentage, which as a percent would be 42.3%. So 42.3% of let's see here, of the variability in calories is, I'm not gonna have enough room here, accounted for by least squares regression line with x equaling sugar. Okay, really tight fit down there, but there it is. All right, guys, that's gonna be it. Hopefully this helps. You also have your other notes, you have other worksheets that you've done, so look through those as well. Those were good. But yeah, I'll sign off for now. If you have any other questions, let me know in class. I'll see you guys later. Bye for now.